All right, it's 2:30, so let's go ahead and begin for the day. Today, we are going to talk about the concepts of instantaneous and average power. So let's consider a generic black box network containing only linear components like resistors, capacitors, and inductors. If we applied a voltage Vs of t across this network's terminals, we would expect to see a voltage V of t across the terminals of our network and a current I of t flowing into our network, where if V of t is of the form Vm cosine omega t plus theta v volts, I of t is expected to be of the form Im cosine omega t plus theta I amps. Instantaneous power, P of t, is simply the product of this voltage V of t and this current I of t, because P is equal to I times V. So over here on the right, I'm going to introduce you guys to another trig identity that we're going to use multiple times throughout today's lecture. That's pretty much it. Okay. That identity says that cosine of angle 1 times the cosine of angle 2 is equal to 1/2 cosine angle 1 minus angle 2 plus 1/2 cosine angle 1 plus angle 2. Okay. I'm pointing this out because we're going to consider this quantity omega t plus theta v to be angle 1 and omega t plus theta I to be angle 2 when we multiply these two sinusoidal signals together. Okay. So V of t multiplied by I of t is going to look like Vm cosine omega t plus theta v multiplied by Im cosine omega t plus theta I. And using that trig identity, this is going to become 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I. This is our generic expression for the instantaneous power absorbed by a network or element or anything like that, right? Simply what the product of our sinusoidal voltage and our sinusoidal current give us, okay? Now, we can break this instantaneous power down into two parts, all right? So let's look at this part over here on the right-hand side real quick. This is an AC contribution to the instantaneous power, okay? And I say that because it still depends on time, right? So the AC contribution is going to be a sinusoid that's oscillating at twice the angular frequency of our voltage and current waveform, because it's oscillating at a frequency of 2 omega, right? The bit on the left is a DC contribution. It's DC because theta V and theta I are constants. Therefore, the cosine of theta V minus theta I is a constant value that's being multiplied by 1/2 a voltage magnitude, which is a constant quantity, times the current. So it's just constant multiplied by constant multiplied by constant. So graphically, what this looks like for a generalized case, and I'm going to do my terrible attempt at drawing a sinusoid, so I'm going to pre-apologize for how bad this is going to look. Here's my instantaneous power P of t. Here is my time t. It's somebody calling me from campus, but I'm in class. So what the DC contribution does is it gives me an offset, which for this particular case, I'm going to consider to be a positive quantity, okay? So the green bit represents my DC contribution. And then superimposed on top of that DC contribution is going to be the AC part, okay? So that might look something like this, okay? So the red bit is the AC part, and it's literally just put on top of that DC offset. So there are a couple of things that we can glean from this graph, all right? The first of which is what's going on in this little region right here and this region, okay? So what happens when, or what does it mean when our instantaneous power is a negative quantity? Right. So the instantaneous power that we've detailed here, our current I of t is flowing into the positive polarity terminal of our linear black box network. So our instantaneous power equation is giving us the power that is absorbed by whatever makes up this network. whenever this instantaneous power is negative, that means our network is supplying power back to the source. Okay. So we should expect to see negative values for instantaneous power in any network that contains inductors and or capacitors. The negative part here represents their energy storage characteristics. They're able to store energy for a brief amount of time and then supply it back to our system. So for brief instances of time, our network here is actually supplying power to our voltage source. Okay. Now, what can we say about the relationship between the AC contribution and the DC contribution here? To me, it looks like half the time the AC signal is above the DC value, and half the time the AC value is below the DC value. So what that means is that the DC portion represents the average power absorbed by the load. I'm going to call this PAVG. Okay. And we can mathematically prove this in a little bit. But for now, just by looking at our graph, we can see that intuitively, the DC contribution represents the average amount of power that's being absorbed, because exactly half the time we are absorbing power greater than that, and exactly half of the time we are supplying power less than that. All right. So let's talk about the concept of average quantities here. Okay. Let's do a more rigorous mathematical definition. If I have a function x of t, and it is periodic, the average value of x of t is given by integrating x of t over exactly one period, and then dividing the results of this integration by the length of the period. Does that make sense? So we take the area under the curve, and then we divide by the duration of the period, and that gives us our average value. So mathematically, our average power will be 1 over t. So in this case, because we're dealing with sinusoidal functions, 1 over t is going to be related to our angular frequency of omega as omega over 2 pi. We're going to integrate from 0 to 2 pi over omega. And we're going to put in our instantaneous power relationship. 1/2 Vm Im cosine theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I dt. So I mentioned previously that the quantity 1/2 Vm Im cosine theta v minus theta I is a constant because all of the parts that make up that are constant values. That means we can actually pull that term out of the integration, which would give us omega over 2 pi multiplied by 1/2 Vm Im cosine theta v minus theta I times the integral from 0 to pi over omega dt plus the integral from 0 to 2 pi over omega of just the AC portion. 1/2 Vm Im cosine twice omega t plus theta v plus theta I dt. Close my brackets off here. So what I've done here, I've taken my constant term out, and I've also split this up effectively into two integrals. So that I'm just integrating two functions and adding them together. Perfectly acceptable. So let's look at that right-hand integral. What does that integral represent? What does any integral represent? The area under the curve. Okay, so let's say that I have a sinusoidal function. And I'm integrating it over exactly one period. What is the area under the curve? 0. Because this area is completely canceled out by this area as long as the limits of my integration are over exactly one period, or really just an integer number of periods, right? Well, that is exactly what this integral represents. We are integrating that sinusoid over one period. And so the area under the curve is equal to 0. Let's look at this left-hand integral, right? We're just integrating time from 0 to 2 pi over omega, which is just like multiplying by a factor of 2 pi over omega. So this integral cancels out this 1 over the period bit, and we're left with 1/2 Vm Im cosine theta v minus theta I, or just the DC contribution to the instantaneous power. Okay. So the math supports our observation from the graph. Okay. All right. So what I'd like to spend the next several-ish minutes doing is developing instantaneous power relationships specifically for capacitors, resistors, and inductors. But before we do that, I want to explain something, okay? This equation, I'm going to put a big box around it right here. Works for everything. It does not matter if it's a resistor, capacitor, inductor, source, etc. This generic equation does not care what the element or combination of elements is, okay? So in a pinch, you can always use this equation. Now, I want to talk about the constituent parts here real quick, okay? our instantaneous power is a time domain quantity because it depends on whatever value time has to evaluate this, okay? Vm and theta v are the magnitude and phase angle of that sinusoidal voltage, V of t, but they're also the magnitude and phase angle of the phasor voltage or the phasor representation of that sinusoidal voltage. Similarly, Im and theta I are the magnitude and phase angle of our time domain current, but they're also the magnitude and phase angle of our frequency domain current. So what that means is that we can analyze our circuits in the frequency domain and then just take the bits out that we need and plug them into this equation, and we'll get the exact same result as if we had worked everything in the time domain. So we still get to use our simple, arguably simple, steady state sinusoidal analysis techniques, even though we are working with time domain quantities, okay? So the expectation here is not to do a bunch of trig and calculus. It is to use complex numbers and then plug those results into this equation. Is that clear? Okay. So Vm is the magnitude part, Im is the magnitude, theta v and theta I are obviously the phase angle. Okay. So for a resistor. Now, when we developed our phasor or frequency domain relationships for resistors, capacitors, and inductors, I put a box around a few relationships. We are going to use those very specific relationships, okay? So we found that for a resistor, the magnitude of the voltage drop across the resistor was simply Im times R, and we found that theta v was equal to theta I. These relationships, again, came from our introduction to phasor domain relationships. So I can use these two relationships to find that the instantaneous power absorbed by a resistor, PR of t, can be expressed as 1/2, let me move this up actually, Vm squared divided by R times 1 plus cosine twice omega t plus twice theta v. So let's talk about where this came from just real quick. I'm going to scroll up to my original equation. So obviously, if Vm is equal to Im times R, then Im is equal to Vm over R. And making that substitution, I have 1/2 Vm times Vm over R, which is where my Vm squared over R bit comes from. Okay, that part's pretty easy to follow. Where that 1 comes from is maybe a little bit more difficult. Okay, so if theta v and theta I are equal, then theta v minus theta I must be 0. And cosine of 0 is just 1. So that's where the 1 comes from. And then we're effectively just distributing a factor of 1/2 Vm Im times 1 plus cosine twice omega t, et cetera. Okay. So let me go back down here. What is very useful about this particular representation is that you only need to know the phasor voltage over the resistor. There are no phasor current relationships in here, right? We don't need to know the magnitude of the current. We don't need to know the phase angle of the current. So if we only know the voltage, we can determine the power absorbed by the resistor. And just for the sake of argument here, we can get an average power relationship as well, where our average power is just the DC portion of this instantaneous power, which is simply 1/2 Vm squared over R. Now, we could express the instantaneous power absorbed by a resistor only in terms of our phasor current as well. That would be Im squared times R multiplied by a factor of 1 plus cosine twice omega t plus twice theta I. And from this relationship, the average power absorbed by a resistor can be expressed as simply 1/2 Im squared times R. So, any questions about where these relationships came from? Anything seem terribly difficult or confusing? All right. Now let's talk about for an inductor. So for inductors, our relationship between the magnitude of the voltage and the magnitude of the current is Vm is equal to omega L times Im. And for the angle part, we have theta V is equal to theta I plus 90 degrees, which means the voltage leads the current by 90 degrees, which you all actually experimentally calculated 2 days ago. That was the purpose of your lab. You verified that there's exactly a 90-degree phase shift. Let me turn off my email thing so it stops popping up. All right. So instantaneous power absorbed by an inductor. All right. Let's look at something here real quick using our original equation. Okay. So if theta V is equal to theta I plus 90 degrees, when we put in theta I plus 90 degrees for theta V, in that first part, we have theta I plus 90 degrees minus theta I, which is just 90 degrees. So what's the cosine of 90 degrees? It's 0, right? So that means our whole DC portion goes away. It's only going to leave us with 1/2 Vm squared over omega L cosine twice omega t plus twice theta V minus 90 degrees. And our average power absorbed by our inductor is 0. Again, we can express the instantaneous power absorbed by an inductor only in terms of the current quantities. That's going to look like 1/2 Im squared omega L cosine twice omega t plus twice theta I plus 90 degrees. And again, our average power is 0. Finally, for a capacitor, we know that Im is equal to omega C multiplied by Vm. And we know that theta I is equal to theta V plus 90 degrees. So what is theta V minus theta I then? Theta V minus theta V minus 90 degrees is negative 90, right? Cosine of negative 90 is also 0. And so that means that the DC portion of our instantaneous power for capacitors is also 0, giving us PC of t is equal to 1/2 Vm squared omega c times the cosine of twice omega t plus twice theta v plus 90 degrees, where our average power is 0. And PC of t is equal to 1/2 Im squared over omega c cosine twice omega t plus twice theta I minus 90 degrees. Those are our instantaneous and average power relationships for resistors, inductors, and capacitors. So before I let you guys take a stab at your in-class assignment, I want to point out one thing here. If you are evaluating any of these expressions at a particular point in time, notice that twice omega t gives you an angle expressed in radians, and the phase angles that we have been dealing with have all been expressed in degrees. So that's going to trip you up when you're doing a calculation. You need to either convert that twice omega t bit to an angle in degrees, or convert all of your phase angles into radians. The conversion factor is simply angle in degrees multiplied by pi over 180 degrees gives you the angle in radians, or the other way around, the angle in radians multiplied by 180 degrees over pi gives you an angle in degrees. So that's how you convert your angles. So typically speaking, when I do these problems, I just say 2 times omega times 180 over pi times t, and then just put my phase angles in. Okay. I work everything in degrees personally because I'm too lazy to change the settings on my calculator. All right, I think that is enough out of me for today. So you can start working on your in-class assignments, and I'll drift around the room and help anybody who needs it.